That was an amazing introduction into PX model, overview of Jürgen Schmidhuber's early research. Let's discuss the PX underlying principles model in details, because if you want to understand how a machine can actually visualize the future.
Right, like not just guessing the immediate next thing, but genuinely planning.
Exactly. Planning a complex, multi-step sequence the exact way a human does, we really have to talk about how artificial intelligence is officially abandoning flat geometry.
It's a huge shift.
It really is. I mean, think about it. Have you ever tried planning like a 10-step project in your head, only to completely lose track of where you were by step 3?
Oh, absolutely. All the time.
Well, that is exactly what happens to our most advanced AI models right now. And today, in this deep dive, we're going to look at the massive mathematical shift that is finally fixing it.
And honestly, it really is a fascinating shift. And tracing it back to that 1992 PMX blueprint you mentioned, it's just the perfect starting point.
Yeah, it sets the stage perfectly.
Right, because if you want to understand the absolute cutting edge of how machines learn the physical world today, you have to look at the lineage. That 1992 blueprint basically set the foundational architecture for the modern predictive world models we see today. Things like the joint embedding predictive architecture, or JPA.
Yeah, and when you put that 1992 blueprint side by side with modern JPA architectures from the 2020s, the shared DNA is just undeniable. I mean, they both rely on this core philosophy of non-generative processing.
Yes, that is the key right there, non-generative.
Right. So instead of taking incredibly complex, raw data, like video frames, and trying to painstakingly draw every single pixel of the future, they map that data strictly into abstract latent spaces.
Exactly. Think of it like trying to remember a movie you just watched. You don't store the exact RGB values of every single pixel of every single frame in your brain.
Right, that would be insane.
It would take an impossible amount of mental energy. You just remember the abstract concepts, like the hero walked into the room, picked up the glass, and dropped it. Both PMX and GPA share this exact predictive intent. They simply evaluate the relationship between a current state and a future state, but entirely in the abstract.
But okay, if they aren't drawing the pixels to prove they know what happens next, how do you stop the AI from just being lazy?
What do you mean by lazy?
Like, how do you prevent it from just saying the future equals the present and predicting the exact same output for everything just to save energy?
Yeah, the collapse problem. That is the big catch. To do this successfully without the model taking those shortcuts, you need a regulatory framework.
Okay.
So in the 1992 PMX, that was an explicit objective function literally designed to penalize sameness. Now, in modern JEPA models, it's an energy function. But functionally, both serve the exact same purpose, information maximization.
So they force the AI to keep working.
Right. They act as an anti-collapse mechanism,
Right.
essentially forcing the model to actually extract meaningful changing variables from the data rather than just collapsing into a single lazy prediction.
Which brings us to what we are really unpacking today for you. We are looking at how we evolve from those early blueprints, and specifically from the modern flat latent spaces they inspired, into the next generation of AI.
The jump to non-Euclidean geometry.
Exactly. We are zeroing in on a highly advanced model called GeoWorld. It completely abandons flat mathematical space and uses curved hyperbolic geometry to solve one of the hardest problems in AI right now, long horizon visual planning.
It is a massive structural shift in how we encode knowledge. But to really appreciate what GeoWorld does, we first need to establish where the industry currently sits. Right now, the baseline state-of-the-art relies on energy-based predictive world models, like VJI2.
Okay, let's break down that term real quick. Energy-based. When we say these models are energy-based, we mean they perform multi-step hierarchical planning by reasoning over a latent energy landscape. They aren't explicitly drawing the future pixel by pixel. They are finding the path of least energy, or basically the least resistance between concepts.
Exactly. And this mirrors biological cognition beautifully. Human infants, for example, well, they don't have language for the first several months of their lives.
Right, obviously.
They learn the mechanics of reality primarily through visual perception. Vision offers this massive, high-bandwidth stream of information compared to language. So building visual world models that can process that immense bandwidth without getting bogged down in rendering pixels is absolutely crucial for achieving anything close to human-level reasoning.
That makes total sense. But while models like V-JEPA 2 are incredibly powerful, they hit a wall the second you ask them to look too far ahead. So okay, let's unpack this. If these models understand abstract concepts so well, Why do they fall apart when trying to plan a sequence of actions deep into the future?
It basically comes down to two major roadblocks. The first is a concept researchers call geometric neglect.
Geometric neglect.
Yeah. In current models, these abstract latent representations, which is the AI's memory of the world, they're typically learned in a flat Euclidean space. Think of standard geometry on a completely flat piece of paper. But the physical world, and specifically the hierarchical relationships between objects and states, it is not flat.
Right. I mean, if you try to draw a massive, sprawling family tree on a single Post-it note, eventually all the names are going to overlap and become a jumbled mess. You are forcing complex hierarchy into a flat space that just can't contain it.
That's a great way to look at it. By forcing high-dimensional hierarchical data into a flat Euclidean space, the model just neglects the underlying geometric structure among those states. The data literally gets crushed.
Which naturally leads to the second roadblock, I imagine.
Yes, the multi-step shortcoming.
Yeah.
Because, acquiring training data of complex multi-step videos is incredibly expensive and difficult.
Oh, for sure.
So these predictive world models are usually only trained on one-step video transitions. Action A leads to action B. But because their mathematical space is flat and crowded, like we just talked about, when you ask them to predict long-horizon events...
Predicting steps C, D, E, and F.
Exactly. Their performance degrades rapidly. They just lose the thread across extended rollouts because they literally cannot mathematically separate the steps clearly.
Wow. And this is where GeoWorld enters the picture. The researchers hypothesized that, well, if flat space is the problem, let's build a geometric world model that explicitly preserves the natural hierarchical structure of reality.
Right, and they do this through something called a hyperbolic JEPA, or H-JEPA.
It literally maps these latent representations from a flat Euclidean space onto curved hyperbolic manifolds. And looking at the source material, the proof is actually in the data.
It really is.
Yeah, they ran extensive experiments on the crosstask and coin datasets, and GeoWorld demonstrated a solid 3% success rate improvement in three-step planning and a 2% success rate improvement in four-step planning compared to V-JEPA 2.
Which is huge.
Yeah, I mean, those might sound like small percentages to some, but in the realm of state-of-the-art AI benchmarking, those are significant leaps. But I have to push back here. Why does simply curving the math make the AI measurably better at planning?
To answer that, we have to look under the hood at how H-JEPA actually maps the future into this curved space. It starts with the projection step.
Okay.
So when the AI's pre-trained encoder looks at raw data and generates a standard flat Euclidean embedding, GeoWorld interprets that flat data strictly as a tangent vector resting at the origin of a curved space.
Okay, I want to stop you right there because the paper gets incredibly dense here. I am looking at the core formula for this projection, and it is just a wall of hyperbolic tangents, square roots, and magnitude bracket.
It has been intense.
It really is. It looks like S sub x comma h equals the hyperbolic tangent of the square root of c times the magnitude of S sub x.
Yeah, and it keeps going from there.
Exactly. As someone reading this, it feels like mathematical alphabet soup. In plain English, what is this math actually doing to the data?
I don't blame you. The notation is very heavy. But instead of getting lost in the formula, just imagine you have a flat, incredibly stretchy sheet of rubber, and you have a bowling ball.
Okay, a rubber sheet and a bowling ball.
Right. That dense formula you're looking at, specifically the exponential map at the origin and that hyperbolic tangent function, is just the mathematical hand taking that flat rubber sheet and smoothly stretching it over the curvature of the bowling ball.
Okay, that actually helps a lot. So it's translating the data from a flat plane to a curved surface. There's a variable in that formula, a lowercase c. What role is that playing in stretching the rubber sheet?
Ah, that variable c is the curvature parameter. And what's brilliant about this architecture is that it's a learnable parameter.
Oh, wow. So the AI adjusts it itself.
Exactly. The AI adjusts it during training. It dictates the constant negative curvature of the model space, so basically the actual mathematical shape being formed, which in this case is called a Poincaré ball model.
Poincaré ball.
Right. So the model is essentially figuring out exactly how curved the space needs to be to fit the data perfectly.
Here's where it gets really interesting because I want to try an analogy to help you, the listener, visualize why we want this Poincaré ball shape instead of a flat plane.
Go for it.
Euclidean space, the flat math, is like a rigid city grid. If you want to move from point A to point B, you are confined to the blocks. The space between things is linear, uniform, and restricted.
Right.
But hyperbolic space, specifically this Poincaré ball, is more like a branching tree. As you move outward from the center, the volume of the space expands exponentially. There is infinitely more room at the edges than there is in the center. But wait, let me ask you this. If the original data is that flat rubber sheet, doesn't stretching it over a curved, exponentially expanding ball severely distort the information?
Is the intuitive fear, absolutely. I mean, you'd think it would warp the data beyond recognition, but the mathematics prevent that. The system uses exponential maps to go from flat to curved, and then it uses logarithmic maps to go from curved back to flat. These dual maps establish a smooth, perfectly invertible correspondence between the flat space and the curved manifold. It's not distorting the data, it's actually giving the data the room it inherently needs.
Room for what exactly?
Room for hierarchy.
Oh.
Yeah. In a flat Euclidean space, hierarchical relationships like understanding that a quote-unquote kitchen contains cabinets, and those cabinets contain cups, well, those concepts just get crushed together.
Because there's no space.
Exactly. If you try to map all of that on a flat grid, the points eventually crowd together. But in hyperbolic space, because the volume grows exponentially as you move outward, it naturally and perfectly encodes those hierarchies.
That makes total sense.
A kitchen is at the center, the cabinets branch out, and the cups branch out infinitely further with plenty of mathematical space between all of them.
So it's basically aligning the AI's internal mathematical space with the true underlying structure of how physical objects and actions relate to each other in the real world.
Precisely. It gives the AI a mental map that actually reflects reality.
That is deeply fascinating. So let's get into the methodology. How do you actually train a massive neural network to think in curved space?
Well, the engine itself is quite robust. The predictor network inside GeoWorld is a transformer model with roughly 300 million parameters.
Okay, that's pretty massive.
Yeah, it has 24 layers, 16 heads, a 10 or 24 dimensional hidden size, and it uses GELU activations. And just to ensure the benchmarks were perfectly fair, the researchers used the exact same frozen visual encoders for both the flat V-JEPA 2 baseline and the curved GeoWorld model.
And those were pre-trained on Video Mix 22M, right?
Exactly. Pre-trained on millions of videos.
Yeah.
So the difference is entirely in how the predictor network handles the data afterward.
Right, and they do that handling through a very distinct two-stage training process. Stage 1 is supervised post-training. From what I understand, the goal here is just to get the model comfortable in the new space. It tries to minimize the Poincare ball hyperbolic distance between what it predicts will happen and what actually happens.
Yep, that's the first step.
And they have to be incredibly careful with how they introduce the AI to this. They use an Atom W optimizer with a specific warm-up constant decay learning rate schedule, warming it up very slowly to, I believe, 4.25 times 10 to the negative 4 with a weight decay of 0.04.
Yes, and that careful warm-up is vital. When you're dealing with curved hyperbolic space, it is highly sensitive. Taking too big of a mathematical step during training means you could literally fall off the curve and break the model's understanding.
Wow.
So they use tiny, precise adjustments to slowly shape the weights.
But stage 1 just gets the baseline predictive model working. Stage 2 is where they tackle the long horizon planning problem, and they do it by introducing something called geometric reinforcement learning, or GRL.
This is the real magic of the paper, honestly. GRL reformulates multi-step planning. Instead of just guessing the next step, it turns planning into the optimization of an energy-based value function over time.
Okay.
It features a smaller learning rate this time around, peaking at 2.0 times 10 to the negative 4 because of higher variance. It uses a discount factor of gamma equals B0.99 and a triangle inequality regularization weight of beta equals 0.1. Basically, it teaches the model that a path with lower hyperbolic energy corresponds to a higher cumulative reward.
Wait, let me stop you there, because usually when we talk about traditional reinforcement learning, it involves training an entirely separate policy network, or, you have to build a distinct reward model to sit there and give the AI a quote-unquote treat when it does something right. Are you saying geometric reinforcement learning skips building a separate reward model entirely?
I am, and that's what makes this architecture so elegant. GRL directly optimizes the predictor's own internal energy-based value representation.
That is wild.
Yeah, by minimizing the hyperbolic energy and enforcing some strict geometric rules, like that triangle inequality we mentioned, it forces the model to generate rollouts that mathematically respect the curve of the space. It doesn't need an external reward model acting as a referee because the geometry of the space itself acts as the guide.
Which brings us perfectly to the visual motif of this entire concept, The energy landscapes. If you've never heard of an energy-based model, it basically defines how compatible different variables are by placing them on an imaginary landscape.
Right.
A lower point on that landscape, like a valley, means higher compatibility. It represents the most likely, most logical future state. The AI basically wants to roll down the hill to the lowest energy point.
Exactly. And this visual of a landscape is the easiest way to understand the flaw of Euclidean models versus the advantage of hyperbolic models.
Let's hear it.
If you mathematically map out the energy landscape of V-JEPA 2, the Euclidean model, it treats all state perturbations uniformly. The result is an energy surface that basically looks like a smooth, circular paraboloid, shallow bowl.
So it's essentially a perfectly flat bathtub.
That is a brilliant way to put it. Yes, it's a flat bathtub.
And a flat bathtub is a nightmare for an optimizer. I mean, if you drop a marble into a bathtub with a perfectly flat bottom, the marble just sits there. It doesn't know which way the drain is.
Precisely. Because the Euclidean space lacks distinct directional structure, the gradients, the slopes that tell the AI which way to go, they are incredibly weak and uninformative.
So the optimizer is practically blind.
Yes. It makes it nearly impossible to discern the correct hierarchical sequence of actions when you are trying to plan 4 or 5 steps ahead. It just wanders aimlessly in the bathtub.
But when you look at the energy landscape of GeoWorld, which is mapped in that curved hyperbolic space, it looks completely different. It isn't a flat bathtub at all. It forms a highly pronounced, curvature-aware basin.
Right.
It looks like a steep funnel. Because states that are hierarchically higher or more complex are positioned mathematically further away, it creates these steep, deep, highly structured slopes.
And those steep slopes act as massive, unmissable signposts for the optimizer. If you drop the marble in the hyperbolic funnel, it immediately knows exactly which way to roll.
That makes perfect sense.
It guides the planning process with incredible efficiency because the optimal path, what mathematicians call the geodesic path, the path of least energy, is just sharply defined by the actual geometry of the space.
Okay, so what does this all mean? Putting this all into perspective, we can trace a clear evolution of how AI understands the world. Let's call it the world model evolution matrix for you to visualize.
Okay, I like that.
Generation 1 was generative models. The goal was predicting actual pixels. There was no latent geometry to speak of, and as a result, the planning horizon was incredibly short. It was reactive, not predictive.
Right. Then we evolved to Generation 2, standard predictive models, which is where V-JEPA 2 sits. The massive leap here was moving the target from drawing pixels to understanding abstract latents.
But the math was still flat.
Exactly. The geometry holding those latents remained a flat Euclidean plane. So while it could plan a little further ahead, the horizon was medium at best, and it just degraded rapidly the further out you tried to look.
And now we're looking at Generation 3, geometric predictive models epitomized by GeoWorld. The target remains those efficient, abstract latents, but the underlying geometry has shifted to a curved hyperbolic manifold.
And the result is a long, highly stable planning horizon.
Exactly. And to actually execute that planning, the model uses something called the cross-entropy method, or CEM. It's an algorithm that leverages this energy-based planning to search for action sequences that perfectly follow those steep, optimal geodesic paths down the hyperbolic funnel we just talked about.
It's a fundamental solution to the degradation problem. By moving from flat planes to curved manifolds, we are finally allowing AI to understand hierarchical relationships in physical states in a way that actually respects reality. The physical world isn't a flat grid. Actions branch out, consequences multiply, and hierarchy expands exponentially.
And hyperbolic math perfectly captures that expansion.
Exactly.
And crucially, it does all of this while saving immense computational effort. The AI isn't wasting millions of cycles trying to hallucinate high-definition video of the future, and it isn't wasting time wandering around a shallow Euclidean bathtub trying to find the next logical step. It simply follows the sharp geometric gradients of the curved space to perform multi-step visual planning with incredible stability.
Seeing how profoundly these artificial world models improve when they abandon flat space for hyperbolic geometry, it raises an incredibly provocative question.
Oh. What's that?
Well, we know that human biological memory and spatial reasoning excel at exactly this kind of hierarchical long horizon planning. We navigate complex, branching realities effortlessly every single day.
Right, without even thinking about it.
Exactly. So if we are now proving mathematically that hyperbolic space is the most efficient, stable way to encode that kind of reality in a neural network, Could it be that human cognition is built the same way?
Wait, really?
Yeah. Are our own mental world models, our memories, our plans, our understanding of cause and effect physically encoded in the topology of our brains using non-Euclidean hyperbolic geometry?
Wow, that is a wild thought to leave on. The idea that the invisible architecture of our own minds might share the exact same curved, exponentially expanding geometry that we are currently engineering into our most advanced AI, it makes you reconsider the shape of your own thoughts next time you plan out your day. Thank you for joining us on this exploration. We encourage you to keep thinking about the invisible geometry shaping both artificial intelligence and your own reality.